7.3, triangle inequalities. And if we find the triangle inequality theorem in our book, it states that the sum of any two side lengths of a triangle is greater than the third side length. And so that's what they wrote here, is that these two side lengths have to be greater than the third, these two have to be greater than that third one, these two have to be greater than that third one. And this kind of makes sense. If we imagine a triangle with a really long side length, I built one here. So this triangle has a really long side length of 20 at the bottom, and then I made the two other sides of this triangle just a value of 2. But the value of 2 isn't long enough, right? These don't even meet. They're too tiny. They're like little T-Rex arms. They don't connect. So these other sides of the triangle needs to be much bigger. How much bigger? Well, they need to at least be able to meet somewhere over here. So they need to add up to some value greater than 20. That's all that triangle inequality theorem says. So we can try some examples. Basically, we can plug in our known values here and test each one of these individually. We can see, oh, is this sum greater than the third? Is this sum greater than the other side? Is this sum greater than the other side? So we'll go ahead and do that here. We have 4, 8, and 10. Is 4 plus 8 greater than 10? Well, that's 12, so we're good there. Is 4 plus 10 greater than 8? Well, that's 14, we're good there. And is 8 plus 10 greater than 4? Yeah, we're good there. So we were good on all three of those. We can go ahead and check this off as yes, it's possible to make a triangle. That's all we were checking there. Okay, we'll do another one here. 7, 9, and 18. 7 plus 18 is greater than 9. 9 plus 18 is greater than 7, so we're good on those. What about 7 plus 9? What's 7 plus 9, Will?
16.
Yep, 16. 7 plus 9 is 16. And is 16 bigger than 18? No.
No.
It's not bigger, so it's smaller. So therefore, these aren't valid side measurements for a triangle. Some of you may have noticed, the book doesn't do this, but there's a huge shortcut. We don't have to check all three, right? Which one of these three will fail? It's always going to be the one with the two smallest values added together, right? So we don't have to check this big value plus medium value, is that bigger than the small value? Well, it's pretty easy. So if you can identify the two smallest values in this triangle check here, then we can simply see if those two smallest values add up to be greater than the largest value. And if they do, then we're good. We can move on. We can say, yes, it's possible to make a triangle. Okay. Can an isosceles triangle have the side lengths of 5, 5, and 10? What's 5 plus 5, really?
10.
Is 10 bigger than 10?
No.
No. So therefore, we can't make a triangle. That easy. Okay, go ahead and do 6 and 7 real quick. So pause here. And hopefully you got no, because 12 plus 4 is 16, which is not greater than 7. And 8 plus 24 is 32, so that's greater than 30. So we're good there. Okay, so now we're going to get a little more specific. Instead of just saying whether or not we can make a triangle, they're going to give us a missing side, and we have to figure out all possible values for that missing side. And as it turns out here, again, we can use that triangle inequality theorem. We can say, oh, we can just plug these known values in, and we can plug our x in. And we can say, is 10 plus 12 greater than x? Is 10 plus x greater than 12? And is x plus 12 greater than 10? The x plus 12 is greater than 10 one is a little weird, because when we subtract 12 from both sides, we get x has to be greater than negative 2. Obviously, all sides are going to be positive values, so x can't be has to be greater than 0 at the very least. So this doesn't actually help us at all. We can kind of just ignore this information. The ones that are useful are the ones that give positive values. So we can check x plus 10 must be greater than 12. Therefore, x must be greater than 2. So that gives us our lower bound. X has to be greater than 2. And the other one is 10 plus 12 has to be greater than x. So 10 plus 12 has to be greater than x. So x's upper bound is 22. And again, I made a little figure for this one. It's this one here. And if I here's my side length of 12. Here's my side length of 10. And this is the side length for FE here. And if I pull it all the way down, this is as small as I can make FE. It's 2, right? I can't get any smaller than this. But as I get bigger, FE gets bigger and bigger and bigger and bigger and bigger and bigger and bigger. What's the maximum value we can get? Well, as it turns out, 22, right? It's actually not 22, it's 22.99999. They just round up to 22. So the upper bound is 22, the lower bound is 2, and we could have gotten that just by subtracting and adding these values here. Okay, we'll try another one. Let's go ahead and try this one. What possible values could we put in here for x? Well, x has to be less than 15 plus 15, right? So upper bound is 30. We know its bare minimum lower bound is 0, but as it turns out, it's 0 for both of those, right? Both of these inequalities. So therefore, x has to be greater than 0 and less than 30. Cool. We're going to do a few more things here. The first is the side angle relationship in triangles, which simply says that the largest angle is opposite the largest side. So essentially, if we know that AC is the largest side, well, even if we don't know the value, we know that angle B here, the opposite angle, is the greatest. Similarly, if we know that some side is the smallest, so if we know that CB here is the smallest, we know that angle A is the smallest angle. So these are relatively simple. For example, this one says, for each triangle, order its angle measurements from least to greatest. This side is smallest, so therefore C is the least, second smallest, then A, and then B. So it'd be CAB. We can do part B here. Same deal. We want to go from least to greatest. The smallest angle is going to be C because it's opposite the smallest side. What's the biggest side, Willie? 20, 21, or 22?
20.
Is the biggest?
22.
22, yeah. So 22 is going to be the largest. So the largest angle will be A. So it'll be CBA for that one there. Okay, go ahead and try 11 and 12 real quick. So pause. So for 11, we get ABC. And for 12, we get BCA. Okay. This one, I'm trusting that you guys can figure this one out. This time we're going to try and figure out which side lengths, or at least order the side lengths from least to greatest. So figure out what side length is the smallest, and then what side length is the biggest. Okay, so hopefully you guys figured out that since this angle is the smallest, the side length that's smallest is BC, right? So it should be BC first, and then finally this angle is the next largest, so AC, and then this angle is the largest, so this side is the largest, AB. Same deal over here. We know that the biggest angle is C, so the hypotenuse here is the largest, and then we know that this side is the next largest, and then finally AC at the end. Least to greatest. Oh, I got that backwards. Yeah, biggest. Yeah, least to greatest. So AC is smallest, CB is next largest, and AB is the greatest. Cool. So we're on the same page. What can you conclude about the side opposite the obtuse angle in an obtuse triangle? Well, if it's an obtuse triangle, that obtuse angle will be the largest angle. Therefore, that opposite side will be the largest one. Yep. Cool. All right, that's it. That's all I got. Have a good one.